Hi, I'm Jim Maher, a product manager for chromatography here at Bio-Rad. Please join me for my upcoming webinar presentation on size exclusion chromatography. I will cover basic principles, matrix selection, and factors affecting resolution. I will provide some important tricks and tips to help you get better results and touch upon some of our latest products to help you with your research. I look forward to seeing you then.
So what is size exclusion chromatography, or SEC? What's the definition of size exclusion chromatography? Size exclusion chromatography, SEC, separates biomolecules in solution based on the size differences of biomolecules as they pass through gel filtration media in a packed bed. The biomolecules do not bind to the SEC stationary phase as they pass through the gel filtration media of the column, so buffer composition does not directly affect the resolution. What are the key characteristics and advantages of size exclusion chromatography? Size exclusion chromatography separates biomolecules by their size. That's the main mechanism of separation. There are principally two types of application areas for size exclusion chromatography. They are high resolution fractionation and group separation, which is used for desalting and buffer exchange of samples. Size exclusion chromatography can separate aggregates from monomers. Size exclusion chromatography is a simple chromatographic technique. It uses isocratic runs or constant run conditions. SEC is a non-adsorptive technique. Molecules do not bind to the media. Separation is unaffected by run conditions. Conditions can be varied to suit sample and downstream needs. It's an alternative orthogonal chromatography technique, and it's faster than dialysis for desalting or buffer exchange of your samples. What are the media characteristics of size exclusion chromatography? The media is a porous matrix in the form of spherical particles. The media is chemically and physically stable, and it is inert. And this inertness gives the properties that these samples don't bind to the media as they pass through the column, don't bind to the stationary phase media as they pass through the column. The porous matrix has variable pore size within the particles. The variability of pore size within the porous matrix of the particles provides the separation range of the size exclusion column. You take size exclusion media or resins and you pack it into a column to form a packed bed. So here I have some pictures of what size exclusion chromatography media looks like. So on the left-hand side is the pore structure inside a particle. You can see that there's variabilities of the channels and spaces within a particle. And on the right-hand side shows actual pictures of particles inside an SEC chromatography column. It means you look at the large round circles, you can see that there's spaces that have voids in them or channels that small particles can enter into these particles and move around. Size exclusion, some size exclusion common liquid definitions are the following. If you take a buffer and fill up a size exclusion column that has the porous particle beads inside of it, the liquid will go outside the particle beads as well as inside the particle beads. And so I'm going to define those different parts of the volume of the liquid is occupying within that size exclusion chromatography column. The volume on the outside of the particles is referred to as the mobile phase or liquid void volume, or commonly referred to as VO, and it's also commonly referred to as the void volume. Liquid inside the pores of the particles is referred to as the stationary phase volume, or VT minus VO. The total column volume is the combination of the stationary phase volume and the mobile phase volume, and is referred to as VT. A complete size exclusion separation takes place in one column volume. This is an important concept to have and I'll be emphasizing this throughout my talk. This slide shows a visual display of the volume definitions that I just reviewed. So on the left-hand side, if you look at the blue volume, this is a representation of a size exclusion column, and the blue represents the void volume, or the volume outside the particles. The picture on the left-hand side, the blue represents the volume inside the porous particles, and the picture in the center represents the total column volume of the volume, and that, of course, is the volume on the outside, inside the volumes. Also notice the definitions that these represent. So on the right-hand side, the void volume is VO, the total column volume is represented by VT, and the stationary phase volume is represented by VT minus VO. So here's another way of representing these column definitions, and this is done on a chromatogram. A chromatogram is the way that experimental information is reported after biomolecules or proteins are separated on a size exclusion column. It is generated by after biomolecules leave the size exclusion column, they go by a detector. If you're looking at proteins, typically you're using a UV detector, and you detect absorbance, UV absorbance of the biomolecules as they pass through the detector. And so if you look, so on the x-axis represents the absorbance, and if you look at the the y-axis represents the absorbance, and the x-axis represents time, or column volume, as the volume of liquid moves past the detector. If you look at this, you can see that VO, the void volume, comes out first, and then the volume in between, or the stationary phase volume, VT minus VO, is second, and then the final portion that goes by the detector that's reported is VT, or the total column volume. And notice also that the tire separation of biomolecules on a size exclusion column takes place in one column volume. Size exclusion chromatography basic run conditions. So initially, for the basic run conditions of a size exclusion column, the column is equilibrated to at least one column volume of liquid buffer initially. Separation is isocratic. Only one buffer solution is required for separation, which makes it a very easy and straightforward technique. A sample volume of less than 4% of the column volume, or 1 to 2%, is ideal, is loaded onto the size exclusion column. Separation of molecules takes place as the sample moves down the column. A complete size exclusion separation takes place in one column volume. Separation by size exclusion chromatography in the column. So how are the different sides of the biomolecules separated as they go through a size exclusion column? Molecules larger than pores cannot diffuse into the pores of the particles and remain in the solution around the beads. And that's represented by the red arrow on the right-hand side, as the large beads can't penetrate the small particles as they move through the column. Smaller particles can penetrate the pores of the particles to various degrees based on their size. And that's represented by the blue arrow. That's the blue arrow on the left-hand side. Access to the pores is limited by steric hindrance, or physical materials. The smaller the molecule, the greater access to the pore space inside the particles. Separation by size exclusion chromatography in the column over time. So here, this just shows you it's an example of how the different size biomolecules are separated as they move through a column. So time 1 on the left-hand side shows the time period immediately after the samples are injected into the column. As you can see, the different size particles are grouped together. The large blue ones, the intermediate green ones, and the small red ones are kind of grouped together. You go to time 2 sometime later as the particles are moving through, as the biomolecules are moving through the column. You can see that there's starting to be separation with the blue molecules which never enter into the pores, moving down further than the column sooner than the other smaller sized molecules, and the other smaller molecules are taking longer to go through the column because depending on their size, they can penetrate into the pores of the beads, which slows them down. And the picture on the left-hand side shows that the three different sized biomolecules have been separated from each other, and the blues have moved down the column furthest down the column, or moving through the column the quickest, and then behind them is the green biomolecules, and then the smallest biomolecules are taking much longer to go through the column. So, but it's a good representation of seeing the separation taking place of the different sizes of the biomolecules. Separation by size exclusion chromatography, the elution order. The general rule of thumb is the smaller molecule, the later it will elute. The larger the molecule, the earlier it will come off or elute from the column for molecules within the separation range of an SEC column. Large molecules that cannot diffuse into the pores elute first from the column, the void volume. They elute in the void volume. Molecules with partial access to the pores of the matrix elute from the column in order of decreasing size. It's a very important concept. Small molecules that have full access to the pores elute last and do not separate from each other. So this is another example of showing us this is a different way of representing how biomolecules of different sizes are separated as they move through a chromatography column. So as you look at the picture on the left-hand side, this is right after the biomolecules are ejected into the column. They're all together. They're all together at the same place in the column. If you look at the picture in the center, as the biomolecules are moving down the columns, the large blue molecules, which do not enter into the particles, are moving through the column much faster and going through the column much more quickly, and are further down the column as the biomolecules are flowing through the column. As you see, the green molecules, generally speaking, are in the middle area. So the green molecules have partial access to the pores, so they can go inside the particles to a limited degree, and then behind them, the biomolecules are taking the longest, or the smallest biomolecules, and that's because they have the greatest access into the internal volume of pores of the particles, and so they go in, and they take much longer to go in and to come out, so they take much longer to move down through a column. So the flow through the column, the liquid is flowing from the top of the picture to the bottom of the picture, as also as the biomolecules are flowing through the column. And on the right-hand side picture, you can see that you have very good separation between the large blue molecules that never entered into the particles, and so they could quickly move down the column and out the column. And behind them are the green biomolecules that have had partial access to the particles, and because of that, they take longer to move down the column than the blue particles, but they move down the column faster than the red biomolecules, which have full access to the internal volume of the pores and take much longer to go into the particles and come out of the particles and move down the column. So this picture is a very good representation of the mechanism of separation of biomolecules as they move to a size exclusion column. And also from this, you can see what we refer to as the elution order, or the order that biomolecules leave a column and are then detected and collected. So this picture is similar to the picture we just went over, but here I want to point out that we're trying to show the formation of the chromatogram here. So here, basically, you have two biomolecule sizes. You have a large biomolecule size and a small biomolecule size. The large ones come off the column first because they can't enter into the inner volume of the particles, the inner pores of the particles, while the small biomolecules can can partially penetrate the pore space, the internal pore space of the particles. So it comes off later. And if you look at the bottom, you see actually the chromatogram being developed, which is developed as these biomolecules leave the column and continue through a tube, continue traveling through a tube and go past a UV detector. And the x-axis represents retention time, so the large molecules come off first, and then they're separated from the smaller molecules. So this also shows you, this is also confirmation of the actual separation taking place. And so this chromatogram also shows that as well. So what I want to point out this time on this chromatogram is the elution order of the different size biomolecules on a chromatogram. So I talked about how this is generated. So if you notice, in this case, retention time and elution volume are interchangeable and mean the same thing. So if you look on the left-hand part of the curve, you see where the sample is injected at that point, and then at the end of the void volume, you have the high molecular weight biomolecules coming off first because they didn't enter into the particles. Then in decreasing size, you have the intermediate size molecular weight biomolecules coming off the column. Coming off the column. And as you call, these are the molecules that have partial access into the internal pore volume of the particles, and so the larger ones, these come off first because they can't penetrate the pores as far as the smaller biomolecules can. And then this represents also the VT minus VO range, and this represents the stationary phase volume. And then the low molecular weight biomolecules elute off the column last because they had full penetration or for all intents and purposes, the greatest penetration into the internal pore space of the particles. And since a elution takes only takes one column volume, they come off by that or before VT. The two main application categories for size exclusion chromatography are high resolution fractionation and group separation. High resolution fractionation typically uses a 30 to 60 centimeter long column. Group separation uses a 10 centimeter long column, or up to a 10 centimeter long column. High resolution fractionation. Size exclusion is used in fractionation mode to separate multiple components or biomolecules in a sample on the basis of the differences of their size. It is used to isolate one or more proteins from each other. Best results are achieved with samples that contain few components or have been partially purified by other chromatography techniques in order to eliminate proteins of similar size that are not of interest. High resolution fractionation is well suited for final polishing step in a purified schema workflow. Monomers can be separated from aggregates, which is difficult to achieve by other techniques. High resolution fractionation can be used after other chromatography techniques since the components of the elution buffer will not affect the final separation. I just want to review one more time since it's a very important principle. We talked about how biomolecules elute off a size exclusion column and the chromatogram that represents that. So just to review, the elution profile of high resolution fractionation is represented by having large molecules leave the column first. So they're equivalent to on this picture high molecular weight. So large molecules leave the column first, followed by smaller molecules in order of their size. The entire separation process takes place as one total column volume of buffer passes through the gel filtration media. Method development for high resolution fractionation. Select the media that will give you the best resolution of the target proteins. To ensure reproducibility in high resolution, select the pre-packed column that is best suited to the volume of the sample that needs to be processed. Select the highest flow rate that maintains resolution and minimizes separation time. Determine the maximum sample volume that can be loaded without reducing resolution. Now I'm going to talk about the other major technique that's used on size exclusion chromatography for biomolecules, and it's called group separation. The purpose of group separation is to remove small molecules from a group of larger molecules. The two primary applications are desalting, the removal of salt or a high concentration of salt from a protein sample, usually done after an ion chromatography separation and before a different chromatography technique, or for downstream applications. The other primary application is buffer exchange. Fast, simple solution for buffer exchange. That is that size exclusion is a fast, simple solution for buffer exchange. It is used to change buffer of a protein sample, usually done between two different chromatography separation techniques, or for a downstream application. Large sample volumes, up to 30% of total column volume, can be applied at high flow rates using broad short columns. So this is different. So group separation, you can load up to 30%, while high resolution fractionation, it's recommended that you load 1 to 2% of your sample in order to get high resolution separation of the different biomolecules from each other. So group separation. So this is a typical chromatogram that you see from group separation. You typically have two peaks. The large molecules are eluted in or just after the void volume. Small molecules such as salt move down the column and have full access to the pores of the particles and do not separate from each other. Small molecules such as salt usually elute just before one total column volume, or VT. Proteins are detected by UV observance, usually at 280, and salts are detected by monitoring the conductivity of the buffer. Factors affecting resolution, and this is principally when you are undertaking high resolution fractionation, you take these into account. Sample volume. Sample volume is very important, if not the most important factor affecting resolution. The ratio of sample volume to column volume is very important. Column dimension and particle size is very important. The smaller the particle size, the better the resolution. Particle size distribution is important. The right packing density provides the best results. So packing density is important. Pore size of the particles. The pore size of the particles determines the selectivity or separation range of a size exclusion column. Using the right pore size for the sample affects resolution. Flow rate. The slower the flow rate, the better the resolution. Viscosity of the sample and buffer. Use samples with low viscosity. Factors affecting resolution. Selectivity. Molecular weight range over which a size exclusion media can separate molecules is the selectivity of the media and column. Resolution. A combination of the selectivity of the media and the efficiency of the media to produce narrow peaks. Most important factors affecting resolution. After choosing a size exclusion media with the correct selectivity, sample volumes and column dimensions become the two most critical parameters that will affect resolution of the sample. And those are very two important points to be familiar with, concepts to be familiar with. And since sample volume is so important, I'm going to review it here in a little more detail. Sample volume. What's the definition of sample volume? So it is the percentage of total column volume that is loaded onto the column. One of the most important factors that affects the resolution of a sample on a size exclusion column. Sample volume is expressed as a percentage of the total column volume. Using smaller sample volumes helps improve resolution, especially if two peaks are close together. For high resolution fractionation, sample volume 0.5 to 4% is recommended. For most high resolution fractionation applications, the sample volume should not exceed 2% of the column volume, and 1% is ideal. For group separation, sample volumes to 30% can be used. SEC column and media preparation and efficiency. High resolution fractionation. If you're undertaking this application type, use 30 to 60 centimeter long SEC columns. Group separation, use up to a 10 centimeter long SEC column. The volume of the packed bed of an SEC column is determined by the sample volume that will be applied to the column. SEC column packing that has bed uniformity and produces high efficiency is essential, particularly for high resolution fractionation. Efficiency is very important in SEC since the separation takes place in only one column volume. Efficiency can be improved by decreasing the particle size of a medium. Highly recommended. It's highly recommended to use SEC columns when possible. Media selectivity and separation range. SEC media today covers a molecular weight separation range from 100 to 80 million, with typical SEC media covering a smaller subset separation range and considerably smaller typically. Pore size and pore size distribution. The different sizes of the pores within an SEC particle determines the separation range of a particular SEC media. So pore size and pore size distribution, the different sizes of the pores within the SEC particle determines the separation range of a particular SEC media. And another way of saying that this represents the stationary phase volume of an SEC column. The separation range of a particular SEC column is also called the selectivity of the media. The selectivity of a gel filtration media depends solely on its pore size distribution and is described by a selectivity curve. Size exclusion media are usually supplied with information on their selectivity or separation range. So here is a representation of a selectivity curve, and so this curve is on the y-axis. You have what's called KAV, which is really represents a normalization of the stationary phase volume. And if you recall, that's after the void volume, and that's where all the separation takes place between the different sizes of the biomolecules, and it ends at BT, one column volume. And on the x-axis, you have the molecular weight or the log of the molecular weight. So this curve is usually generated by using known standards, and you run them on the column, and you see where they elute from the column. Since this is the stationary phase volume, the elution goes from 0 to 1. So the part of the biomolecules that are closer to 0 elute first. The ones that elute closer to 1 elute last. And you then plot these biomolecules where they elute, when they elute the column, or when they come off the column, to their actual molecular weight, and you generate a protein selectivity curve. The selectivity of gel filtration media depends solely on its pore size and distribution, and is described by a selectivity curve. Selectivity curves are usually linear over the range of KAV equals 0.1 to KAV equals 0.7. And it is this part of the curve that is used to determine the fractionation range of a gel filtration medium. What is fractionation range? Well, fractionation range defines the range of molecular weights that have partial access to the pores of the matrix. Molecules within this range should be separated by high-resolution fractionation. The exclusion limit for size exclusion media, also determined from the selectivity curve, indicates the size of the molecules that are excluded from the pores of the matrix and therefore elute in the void volume. So here we have an example of a selectivity curve. So on the if you note, on the y-axis we have KAV, and on the x-axis we have the log of the molecular weight of the biomolecules, and we have a curve that's been generated as they eluted from the column. It was recorded where they eluted and what their molecular weight was. And if you look at 0, if you go to the y-axis and look and draw lines from 0.1 horizontally across and a line from 0.7 horizontally across from KAV, and where they intersect with the actual curve itself of the biomolecules eluting from the column, you can determine the fractionation range, or the range of molecular weights of biomolecules that can be separated on the column. So within this range, biomolecules within this range can be separated from each other. So and so as you can see, there are certain biomolecules that are too small to be separated. Those that are furthest to the left on the left part of the curve, and there's also biomolecules on the right-hand side of the curve that are too large that always stay in the void volume, and those molecules that are in what represent what's called the exclusion limit, which are less than 0.1 keV, and those molecules cannot be separated from each other on a size exclusion column, and they are excluded. Since they're excluded from going into the columns and being separated from each other, you can determine what this molecular weight where biomolecules that are larger than this amount can no longer be separated. Okay, now for this part of the talk, I'm going to kind of review of running your sample on an SEC column. How do you prepare your sample? What are recommended buffer and running conditions and flow rates? Sample preparation. Correct sample preparation is extremely important for SEC. Simple steps to clarify a sample before applying it to an SEC column will avoid the risk of blockage, reduce the need for stringent wash procedures, and extend the life of the SEC column. Samples must be clean and free of particulate matter, particularly when using particle sizes of 34 microns or less. Sample clarification includes both steps below: centrifugation and filtration. Size exclusion chromatography is independent of sample mass, and sample concentrations up to approximately 70 milligrams per mil. Sometimes you hear people say no more than 50 to be on the safe side. Highly viscous samples can cause significant reduction of resolution. Running buffer composition. For your running buffer composition, you should select a buffer and a pH that are compatible with protein stability and activity, and in which the product of interest should be collected. A significant advantage of size exclusion media is that the conditions can be varied to suit the type of sample or requirements for further purifications, analysis, or storage without altering the SEC separation. SEC separations can be undertaken in the presence of essential ions, cofactors, detergents, urea, and high or low ionic strength at 37 degrees C, or in the cold room, according to the requirements of the experiment. Purified proteins can be collected in any chosen buffer. Sample application. How do you apply the sample to the column, to the SEC column? A sample volume of less than 4% of the column volume, 1 to 2% is ideal, is loaded onto the size exclusion column. The sample should not be diluted when loaded onto the column. The top of the SEC column bed is not disturbed during sample application, or the top of the top of the SEC column should not be disturbed during sample application. Samples can be loaded automatically or manually. Apply samples onto the SEC column using a chromatography system, periscope pump, or syringe. Use your chromatography system for an Enrich SEC 10 micron type column. Elution and flow rates. Samples are eluted isochronically from a size exclusion column, using the sample buffer and using the same sample and running conditions throughout the entire run, which makes it simple and straightforward. The entire separation takes place as one column volume. A buffer moves through the column, so use flow rates that allow molecules to diffuse in and out of the matrix of the particles in order to achieve a separation, which is very important, and which I've reviewed why that is very important. The goal for a separation is to achieve the highest possible resolution in the shortest possible time. Resolution decreases with higher flow rates. Maximum resolution is attained with a long column and a low flow rate. The fastest run is attained with a short column and a high flow rate. If peaks are well separated at a low flow rate, increase the flow rate or shorten the column to save time. Care size exclusion columns for separations. Always use filtered buffers and samples to reduce the need for column maintenance. Always use well-to-gas buffers to avoid the formation of air bubbles in the packed column during the run. Buffers, pre-packed columns, and samples should be kept at the same temperature to prevent air bubbles from forming in the column. Filter cleaning solutions before use, and always re-equilibrate the column with 2 to 3 column volumes of buffer before the next separation. Now I'm going to talk about our new Enrich size exclusion columns. We are in the process of introducing these new size exclusion columns, Enrich size exclusion columns provide high resolution separation and purification of biomolecules, principally for proteins. They're able to achieve this since they have a 10 micron particle size. As we recall, the smaller the particle size, the higher the resolution. They're ideal for protein applications. They provide superior quality, reproducible separations. They have lower back pressure than similar media. They have a polymethacrylate stationary phase that allows us to run at higher flow rates. The Enrich 650 column can be ran at 2 millimeters per minute. The Enrich 70 column can be ran at 1.5 millimeters per minute. The Enrich size exclusion columns, or the Enrich SEC columns, have short separation times because of their high flow rate capability. For an example, a 24 mil volume SEC column can complete a high resolution separation in less than 30 minutes. Stability from pH 2 to, they also have pH stability from 2 to 13. Okay, what are the size exclusion column types? Well, we're introducing two types of size exclusion columns. There's the Enrich SEC 650 column that has a separation range of 5,000 to 650,000 Daltons. And we also an Enrich SEC 70 column that's a separation range of 500 to 70,000 Daltons. Enrich SEC 650 and 70 columns have in common that they have 10 micron particle size beads. They have a 10 by 300 millimeter format, and they have 24 millimeter column volume. And this chromatogram shows very high resolution of a complex protein sample that was ran on an Enrich size exclusion 650 column. And as you can see, the peaks are well separated from each other, and it just shows really great high resolution. These are really great high quality products. They will provide fantastic high resolution with very short separation time. This concludes my talk. I really appreciate the fact that that you guys have been willing to listen to me for the last half hour, and I really do appreciate it.
Thanks, Jim, for that great introduction into the basic principles of the SEC columns, and also for that introduction into the new Enrich columns that are going to be available soon. At this point, I'd like to open it up to any questions. If you have any questions, feel free to type them into the chat to address them to Laura Moriarty, and I will be more than happy to read them to Jim and have those questions answered. Otherwise, feel free to contact us. I believe you have Laura's email address, so forward any questions you have to her as well. At this point, Jim, actually, I did have a question from an earlier session. When are these columns going to be made available?
It'll be very shortly, in approximately about a month's time.
About a month? Oh, excellent. Okay. And will there be any other upcoming column types in the Enrich family as well?
Yes. We also, at the same time, will be introducing some new ion exchange columns. They're called the Enrich Q and S. And these are also very high resolution columns that have 10 micron size beads. So they're able to provide exceptionally high resolution separation for protein samples.
Excellent. Sounds good. So does anybody have any other questions that they want to ask Jim through the chat? If there are no other questions, I think we'll go ahead and we can end the meeting at this point. Feel free to contact any of your local Bio-Rad representatives if you have any further questions on anything you saw regarding chromatography or the Enrich columns. And at this point, I think we're going to go ahead and end the meeting and the webinar. But thank you again for your attention and your participation, and we hope to hear from you soon. Thanks, everybody. Bye.